Welcome back. In this video, we are going to continue talking about transformations of sine and cosine functions, graphing them. We've already looked at graphing sine and cosine functions where there's been a vertical stretch or a horizontal stretch. And now we'll be adding into the mix a horizontal shift and vertical shift. So first off, when we're given an equation of a sine function or a cosine function in this form, we'll first begin by rewriting it in this form. And the reason that we'll do that is so that it makes it clear exactly how much of a shift we have horizontally speaking. Now, when we're talking about sine and cosine functions, we have a special name for that horizontal shift. We call that the phase shift. So when I have my trig function and it's simplified and written in this form, once I've factored out the b that's in front of the x, the number that's left behind, c over b, that is my horizontal shift. In other words, that's my phase shift. I would say for this that it's a phase shift of positive c over b, because we'd be shifting our graph to the right by c over b. So we now have a couple of things that we can add on. We have, as before, for a trig function, once we've written it in that form, we know that the amplitude is absolute value of a. We know period is 2 pi divided by the absolute value of b. And we also have now a phase shift of c over b and also a vertical shift of d. And of course, just like before, if d was positive, we'd be shifting our graph upwards, and if d were negative, we'd be shifting our graph downwards. All right, let's do an example. We've got a function y equals -5 sine 3x minus pi. We want to know the amplitude, period, and phase shift. And before I do any of that, I am going to rewrite my trig function by factoring out that 3, and that will leave behind x minus pi over 3. All right, so we can now identify right away what the amplitude is. We know that the amplitude should be the absolute value of -5, which is, of course, just 5. And for the period, we know that for the period that should be 2 pi divided by the number that we just factored out, that 3, so 2 pi over 3. Since the 3 is positive, I didn't bother putting absolute values on it. If it was a -3, of course, take absolute value and make it a positive 3 when you're calculating the period. And then finally, for the phase shift, if we're looking at what we have here, we are shifting our graph to the right by pi over 3, and so that means that we have a phase shift that is positive and positive pi over 3. Okay, so going from a function, finding the amplitude, period, and phase shift, and of course we should be able to do the reverse. Starting with a description of an amplitude, a period, and a phase shift, come up with the equation of a function with those properties. So I'm going to work my way from easiest to most involved. The easiest part, of course, is the amplitude. We know if it's got an amplitude of 7, that tells you that the absolute value of a must be 7. So you have two choices here. Either you could take a being 7 or a being -7. I'm going to choose to use a value of a being 7. And now, next up, if we're thinking about the period of our graph, we say that the period is 3 pi. We know that if the period is 3 pi and period is 2 pi divided by absolute value of b, now here I'm going to make my choice in advance. Absolute value of b could either be positive or negative. I'm going to choose to use a positive value for b here. And then if I were to solve this equation, if I were to bring the b up to the right side and divide the other side by the 3 pi, I could find out that my value for b should be 2/3. So I'll just summarize that over here in the corner. B is 2/3. thirds. And then finally, our phase shift of negative pi over 2. Reminder that when we have our equation written in this form, that our phase shift would be c over b. So, going backwards, then we'd say, since our phase shift is supposed to be negative pi over 2, then c over b should be negative pi over 2. And now we will put it all together. We're looking for our cosine function, and the cosine function is y equals a times cosine of bracket b 2/3 times x minus our phase shift, negative pi over 2. Now, of course, I'm going to simplify this. I mean, x minus negative pi over 2 is the same thing as x plus positive pi over 2. And I'm also going to multiply that 2/3 into the bracket. So when I do that, I'll say then that y is 7 cosine of 2/3 times x, and 2/3 times pi over 2, that would be pi over 3. Now, the follow-up question, which was, can we find a second equation of a cosine function with the same properties? And I've kind of been hinting all along that the answer is yes, because remember at the beginning I said that a could be positive or it could be negative, which means I could have chosen to use a value of a that was negative 7, in which case my equation would have been negative 7 cos 2/3 x. I also could have chosen b to be negative. I could have had, let's say, a reflection in the y-axis. And so I could have had a negative 2/3 in my equation rather than a positive 2/3. And of course, the third thing that I could add to make a different equation with the same properties would be to add some sort of a vertical shift. So for example, if I added a vertical shift of 1, adding the plus 1 at the end, that wouldn't change the amplitude, period, or phase shift. So not only is there a second equation that we could come up with, actually we could come up with infinitely many different equations of cosine functions, all with the same amplitude, period, and phase shift. All right, so now the big pressing question is, how do we graph these functions? And it's basically a follow-up to what we did back in 7.6. So first thing that we'll do is rewrite our function in that standardized form where we'll factor the b out. And we'll do the same thing that we did in 7.6. We'll use the symmetry properties of sine and cosine to make it a positive value for b. And the reason that we want to do that, of course, is that means one less transformation for us to have to take care of. We won't have to worry about reflections in the y-axis if we've got b being positive. So the plan now is to do our graph in 2 stages. First, we look at the simplified version of our sine function or cosine function without the phase shift and without the vertical shift. We look at that a sine bx or a cos bx. And we find the 5 key points. So basically, we do the work as we did in section 7.6. And once we've done that, then we just apply the phase shift and vertical shift, adding c over b to all the x values and adding d to all the y values. Of course, keep in mind that c over b could be positive or negative. If it's a shift to the right, it's a positive c over b. If it's a negative value for c over b, it's a shift to the left. And same thing for d. If it's a positive value for d, we're shifting upwards. And if it's a negative value for d, we are shifting downwards. So once we've taken our 5 key points and then adjusted them for the phase shift and vertical shift, then plot those 5 points, connect the dots, and then use periodicity to make another cycle if you need one. Now, let us give an example. So we're looking to do 2 cycles of this sine graph, and I'm going to do, for the first step here, rewriting my function. So I would rewrite this as 4 sine of negative 5. We'll factor that out, leaving x plus pi over 5. All right, good. And because we know that sine is an odd function, sine of negative theta is negative sine of theta. So in other words, that negative in front of the 5, I can take that out. That would be negative 4 sine of 5 times x plus pi over 5. All right. So looking at this, we can see that at the very end of it, we will have a phase shift of negative pi over 5. We'll be shifting our graph to the left by pi over 5. So once we've done our 5 key points, we will subtract pi over 5 from all of our x coordinates. So let's figure out where our 5 key points are. And to do that, of course, we need to figure out our period. And our period here would be 2 pi divided by b, in this case 5. So our period is 2 pi over 5. And next we figure out the length of our subintervals. And we do that by, remember, taking our period and dividing it into 4 equal-sized pieces, or in other words, taking our period and multiplying by a quarter, which once I simplify that, I find that the length of my subintervals is pi over 10. So in other words, my tick marks are going to start at x value of 0 and go up by pi over 10. So let's do that. I'll make a little table here for my x values. Could be 0 or pi over 10 or 2 pi over 10. I'm not simplifying these numbers just yet because, of course, I'm going to be doing my phase shift after, and so I'll save the simplification for the end of it all. 3 pi over 10, 4 pi over 10. I'm just going to make that look a little bit nicer. All right, and I'll just draw some lines in here to make a little table. There we go. And now for our y values. Reminding ourselves, of course, that we're looking at a sine function, and for a sine function we begin with the y value of 0, then go up to a, then to 0, then to negative a, then back to 0. And here the value of a is negative 4. So we start off with y value of 0, then a, which is negative 4, then 0, then negative a, which is positive 4, then back to 0. Those would be the 5 key points for our sine function without the phase shift. Now, with the phase shift, we are going to have to subtract pi over 5 from all of our x coordinates, reminding ourselves that we were looking at this function where the phase shift is pi over 5 to the left, so we'll be subtracting pi over 5 from all of our x values. And so now let's do that. We have for our x values 0 minus pi over 5, that's negative pi over 5. Pi over 10 minus pi over 5. If you're having trouble thinking of how to do the calculations for this, you can sort of ignore the pi for now. So for example, if I'm thinking about pi over 10 minus pi over 5, I could think about that as 1/10 minus 1/5. And 1/10 minus 1/5 is negative a tenth. So I should have negative pi tenths. And then we have 2 pi over 10 minus pi over 5. 2 pi over 10 minus pi over 5, or 2/10 minus 1/5. Well, that's 0. 3 pi over 10 minus pi over 5. That's pi over 10. And 4 pi over 10 minus pi over 5. That is pi over 5. Okay, and our y values are not going to change because, of course, there was no vertical shift for this graph. There was just a horizontal shift, a phase shift. So our tick marks are still going up by pi over 10. The lengths of our subintervals haven't changed. We just have taken the original 5 points and shifted them to the left by pi over 5. And so now let us plot our points. So our points begin, and I've already taken the liberty here of making my x-axis and y-axis drawn out with all the tick marks written in. Our y values were to be starting at negative pi over 5 at 0, and then a, which was negative 4, and then back to 0, then negative a, which was positive 4, then back to 0. And there we go. And now I can continue on. The periodicity tells me that my graph would go back down to negative 4, then back to 0, then up to 4, then back down to 0. And there we go. Now these points, I really should be labeling them. So for example, I should label this point as pi over 2 and 4, this one as 3 pi over 10 and negative 4, and pi over 10 and 4, and negative pi over 10, negative 4. The last thing I should be doing for this would be to label my graph, and I'll label it with the original equation being the y equals 4 sine negative 5x minus pi. So that's what I'll label my graph with. There we go. And there we go. We've graphed our transformed sine function where there was a vertical stretch, there was a horizontal compression, there was also a phase shift. All right, good work, everyone. Take yourself a little bit of a break. And in the next video, when we come back, we will do a few more examples, and we'll look at some where there's also a vertical shift as well. All right, we'll see you in a few.